Good morning, students. Today we are going to discuss our new topic, that is calorimetry. Okay, till now we have discussed the topic of the thermal stresses and strains. Okay, and then we have discussed the heat capacity and also the specific heat capacity and the molar specific heat capacity. Okay, now today we are going to discuss calorimetry. Okay, a system is said to be isolated if no exchange or transfer of heat occurs between the system and its surroundings. First, we are going to discuss what is the isolated system. Okay, if there is a system, okay, which is isolated from the surrounding, that means nothing can go inside this system and nothing can go outside from this system. Okay, that means transfer of heat is not possible. No exchange or transfer of heat occurs between the system and the surrounding. Okay, that means heat can't be transferred from this system. Then this type of system is called isolated system. Okay, so when different parts of an isolated system are at different temperature, a quantity of heat transfers from the part at a higher temperature to the part at lower temperature. Okay, then the heat lost by the part at higher temperature will be obviously equals to the heat gained by the part at the lower temperature. Okay, so this is an isolated system and this part is at higher temperature and this part is at lower temperature. As we know that this is an isolated system, that means no heat can go inside and no heat can go outside. That means only the heat inside this system can be transferred from one part of this to another part of this system only. Okay, so for example, if this part is at higher temperature and this part is at lower temperature, we know that heat transfers from the higher temperature to the lower temperature. That means from this part heat will be transferred to the lower part or at the temperature at the lower temperature. Okay, that means whatever heat will be released by this part, that amount of heat will be gained by this part now, because none of the heat is going outside. Okay, all the heat is going to transfer within this system only. Okay, so whatever the heat will be released by the upper part now, that equal amount of heat will be gained by the lower part. Okay, and this is called the principle of the calorimetry, that the heat lost by the part at a higher temperature is equal to the heat gained by the part at the lower temperature. Okay, so calorimetry means measurement of heat when a body at higher temperature is brought in contact with another body at a lower temperature, and the heat lost by the hot body is equal to the heat gained by the cooler body, provided no heat is allowed to escape to the surroundings. Okay, so a device in which heat measurement can be done is called the calorimeter. Okay, so it is a device in which we can measure the heat, how much heat is transferred from the higher temperature to the lower temperature part. Okay, because none of the heat is going to get out from the system. Okay, so all the heat is inside the system only. That means we can measure how much heat is transferred from one part to the another. Okay, and that device is called the calorimeter, in which we can measure this temperature. Okay, so it consists of a metallic vessel and stirrer of the same material. This is the calorimeter. Okay, in this is the metallic vessel we are using here. It is a copper and also a stirrer that is also made up of copper. Okay, so it consists of a metallic vessel and stirrer of same material like copper or aluminium. The vessel is kept inside a wooden jacket which contains heat insulating material like glass wool. Heat insulating material, that means that material will not allow the transfer of heat from the inner part to the surrounding. Okay, This is our copper vessel, okay, and this is the wooden jacket, and this is the heat insulating material which will stop heat from transfer to from inner to the outer part. Okay, it is made up of glass wool. Okay, so the vessel is kept inside a wooden jacket which contains heat insulating material like glass wool, etc. The outer jacket acts as the heat shield and reduces the heat loss from the inner vessel. There is an opening in the outer jacket through which a mercury thermometer can be inserted into the calorimeter. Okay, there is an opening through which we can insert an thermometer. This is the thermometer which we can insert in the calorimeter. Okay, and then we can measure the temperature. The following example provides a method by which the specific heat capacity of a given solid can be determined by using the principle heat gained is equal to the heat lost. Okay, so what is the principle? The two bodies of masses m1 and m2 having specific heats, for example s1 and s2, for temperature difference delta T. Okay, then heat lost by the hotter body will be equals to the heat gained by the colder body, and we know that heat change in heat will be equals to m as delta T. How? Because what was the specific heat? Specific heat was 1 by m delta Q by delta T, na? This was our specific heat. So what will be the value of delta Q now? Delta Q will be S into m into delta T, that is m is delta T. Okay, so this is the change in heat for the first body. Okay, and that means this heat is lost by the first body, because finally they both will attain, the body m1 and m2 will attain the same temperature now. So some amount this if m1 is at the higher temperature, then some amount of heat will be lost by the m1, and that heat is given to the m2. Okay, so equal amount of heat will be changed in both. This amount of heat will be lost by the hotter body, and this amount of heat will be gained by the colder body. Okay, so this is the example. A sphere of 0.047 kg aluminium is placed for sufficient time in a vessel containing a boiling water so that the sphere is at 100 degrees Celsius. This thing was done just to make the temperature of sphere of 100 degrees Celsius. Okay, and nothing is other significance for this. Okay, this thing is done just for making the temperature of sphere as 100 degrees Celsius. Now it is then immediately transferred to 0.14 kg copper calorimeter containing 0.25 kg of water at 20 degrees Celsius. Okay, so there was a calorimeter having mass 0.14 kg, and in that previously water was placed having 0.25 kg mass, and at the temperature of the water was 20 degrees Celsius. Previously this water was inside the calorimeter. Okay, before putting the sphere. Okay, now the temperature of water rises to attains a steady state at 23 degrees Celsius. That means after inserting this aluminium sphere, the temperature of water rises and it reaches the steady state, that is 23 degrees Celsius. That means the temperature of aluminium also decreased now, because they both will attain the steady state at same temperature. After inserting them and after stirring them with the help of stirrer, they will attain the same temperature. Okay, and here it is given that 23 degrees Celsius temperature will be the final steady state temperature of both the bodies. Okay, now in solving this example, we shall use the fact that a steady state heat given by an aluminium sphere will be equal to the heat absorbed by the water and the calorimeter. Okay, they are saying that in this we will use the principle of the calorimeter, that how much heat will be lost by this aluminum sphere at 100 degrees Celsius will be gained by the calorimeter and the water. Both will gain that heat. Okay, calorimeter will also gain the heat. Okay, so mass of the aluminum sphere was given 0.047 kg, and the temperature of the aluminum sphere, we have reached the aluminum sphere at 100 degrees Celsius temperature na, by boiling it with the water, and final temperature should be 23 degrees Celsius. We know that. So what is the change in temperature? It is 100 minus 23, that is 77 degree is delta T here. And specific heat capacity of aluminium is denoted by SAL. Okay, then the amount of heat lost by the aluminium will be ms delta T, that means 0.047 kg into S aluminium into 77 degree Celsius. Mass of water was 0.25 kg and mass of calorimeter was 0.14 kg, because calorimeter will also absorb some heat. Heat will not be released in surrounding, but heat will be gained by calorimeter. Don't think that's how calorimeter is gaining heat. Calorimeter is also made up of copper, na? So calorimeter will gain heat, but the surrounding heat lost in surrounding will not be there. Calorimeter will gain heat because in surrounding we have covered it with the glass wool and then what, a wooden jacket. So surrounding will not gain the heat, but calorimeter will gain the heat. So initial temperature of water and calorimeter was 20 degrees Celsius. Both were at 20 degrees Celsius now, because water was inside the calorimeter. And the final temperature of the mixture will be 23 degrees Celsius. So a change in temperature for both these will be 3 degrees Celsius. Now specific heat of water we know 4187, or we can write it as 4.18 into 10 raised to power 3 joule per kg per Kelvin. And specific heat capacity of the calorimeter is that is made up of copper na, that is given by 0.386 into 10 raised to power 3 joule per kg per Kelvin. What we have to calculate? We have to calculate the specific heat capacity of aluminium. Okay, so we have to remember the specific heat capacity of water, and for copper it will be given to you in question. Okay, now the amount of heat gained by water and calorimeter will be equals to this ms delta T for water plus ms delta T for the copper calorimeter. Okay, here delta T is same for both of them, because both of them, the calorimeter and the water, were previously on 20 degrees Celsius and then their temperature increased to 23 degrees Celsius. That means the temperature difference was same for both of them. Okay, now put all the values here and you will get the value. Okay, and this value will be equals to the heat lost by the aluminium, and this will be the heat lost by the aluminium. This will be equals to this complete value, and after solving this we will get the specific heat capacity of aluminium. It is in 0.911 in kilojoule. Okay, this was the numerical to understand the concept of the calorimeter. Our next topic is change of state. Matter normally exists in three states. We know that: solid, liquid and gas. A transition from one of these states to another is called the change of state. When matter changes one state from another, it is called the change of state. Two common changes of states are solid to liquid and liquid to gas. Normally solid changes to liquid and liquid changes to gas, and vice versa also. Liquids also changes to solids and gases also changes to liquids. These changes can occur when the exchange of heat takes place. Correct? When these changes will be occur, these changes can only be occur if the exchange of heats takes place. Okay, that means heat is lost or heat is gained between the substance and the surroundings. To study the change of state on heating or cooling, let us perform the following activity. When you are writing the note, or if you are writing in exam also na, you don't need to write these activities, or if you are copying them, you can also cut this portion. Okay, so take some cubes of ice in a beaker, because this is just an example to understand the concept. Take some cubes of ice in a beaker. Note the temperature of ice. Start heating it slowly on a constant heat source. Then note the temperature after every minute. Continuously stir the mixture of water and ice. First we have taken cubes of ice in a beaker. Then we have noted the temperature of ice. Then we have started heating it slowly on a constant heat source. Then we have noted the temperature after every minute. Now continuously stir the mixture of water and ice. Draw a graph between temperature and time. You will observe that no change in the temperature as long as there is ice in the beaker. This is the graph we have created. We will understand this graph now. You will observe that no change in the temperature as long as there is ice in the beaker. In the above process, the temperature of the system doesn't change even though heat is being continuously supplied. The heat supplied is being utilized in changing the state from solid to liquid. What we will see? We will see that when ice was there at 0 degree Celsius, okay, then we have started heating that ice. Okay, this was ice and we have started heating it, and this was at 0 degree Celsius. Okay, then if we have started heating it with the continuous supply of heat now, then the temperature of ice was not rising. We were actually measuring the temperature after every minute now, but when we have started this ice at 0 degree Celsius, after heating it the temperature was not rising. Okay, but we were giving it heat continuously. Heat was supplying continuously. The heat supplied is being utilized in changing the state from solid to liquid, that is from ice to water. So where was that heat going? That heat was going in changing the state from solid to liquid, that is from ice to water. Okay, that I told you that latent heat is there, that is the hidden heat which will not increase the temperature. Okay, so when time was increasing, okay, temperature was not increasing, temperature was same, and as time was increasing we were giving it heat. Okay, so till this time we have given it heat, but this much heat has not increased the temperature of the ice. Okay, that was only changing the phase or changing the state from solid to liquid. Okay, so the change of state from solid to liquid is called the melting, and this situation is called melting, and from liquid to solid it is called fusion. If we are changing from solid to liquid, it will called melting, and if we are changing from liquid to solid it is called fusion. That means if water is converted into ice it is called fusion. It is observed that the temperature remains constant until the entire amount of solid substance melts. Okay, the temperature will remain same 0 degree Celsius until the complete solid will be completed into the liquid. That is, both the solid and the liquid states of the substance coexist in the thermal equilibrium during the change of the state from solid to liquid. When the state is changing, the liquid state and the solid state will coexist. That means they exist at the same time in thermal equilibrium. That means their temperature will be same. Thermal equilibrium means the temperature will be same during the change of states from solid to liquid. The temperature at which the solid and the liquid states of the substance is in thermal equilibrium with each other is called the melting point. Okay, at which point the temperature of the liquid and solid is same, or at which point the liquid is converted into the solid or solid is converted into the liquid. For water it is 0 degree Celsius. At 0 degree Celsius ice is converted into the water and water is converted into the ice now. So that is the melting point of water. Okay, it is characteristics of the substance. It also depends on the pressure. Okay, this melting point also depends on the pressure. The melting point of substance at a standard atmospheric pressure is called normal melting point. If we are using the standard atmospheric pressure now, then that is called the normal melting point. 0 degree Celsius is the normal melting point for the water. Let us do the following activity to understand the process of melting of ice. Now, take a slab of ice, take a metallic wire and fix two blocks, say 5 kg each. Okay, this is the, see, this is ice block and this is the metallic wire we have taken, and these are the two blocks of 5 kg each. Okay, see, take a slab of ice, take a metallic wire and fix two blocks, say 5 kg each, at its ends. Put the wire over the slab as shown in the figure. We will put this wire over this slab. Okay, then what will happen? You will observe that the wire will pass through the ice slab. This happens due to the fact that just below the wire, ice melts at lower temperature due to increase in pressure. What will happen now? This wire will pass through the slab. Okay, and the slab will not melt. This will happen because this is the wire over the ice slab. Okay, so the surface of the ice just below this wire, that will experience more pressure due to these forces. Due to these forces, the surface will experience more pressure, and due to that pressure, the ice will start melting at even lower temperature. Okay, at even lower temperature that ice will start melting. Okay, so this happens due to the fact that just below the wire, ice melts at lower temperature due to increase in pressure. That means if we will increase the pressure, the melting point will get lower. Okay, so when the wire has passed, water above the wire freezes again. When this wire will be passed through the surfaces now, so the surface above the wire will again start freezing because that surface is now not feeling any extra pressure now that is on atmospheric pressure. So again its melting point will become 0 degree Celsius, but the surface which is lower the metallic wire that will feel extra pressure, so that melting point will decrease, and due to that the ice will melt. Okay, before the 0 degree Celsius the ice will melt because that is feeling some extra pressure. So due to the increase in the pressure, the melting point of ice got decreased. Ice starts melting at lower temperature. Okay, ice melts at lower temperature due to increase in pressure. So when the wire has passed, water above the wire freezes again. Thus the wire passes through the slab and the slab doesn't split. Okay, this phenomena of refreezing is called regulation. This phenomena is called regulation. Okay, skating is possible also due to the formation of water under the skate. When we are skating, we are applying some pressure on the ice, correct? So due to that phenomena, the pressure is applicable on that, and where we are applying the pressure on that, ice is converted into the water. Only on that portion ice is converted into the water, and that water, so skating is possible on snow due to the formation of water under the skates. The water is formed in the skates, so it is possible to slide. So water formed due to the increase in pressure and it acts as a lubricant. Due to some lubrication we are able to slide over the snow. Okay, now after the whole of ice gets converted into water, and as we continue further heating, we shall see that temperature begins to rise. The temperature keeps on rising till it reaches nearly 100 degrees Celsius. In this figure, after the whole ice is converted into the water then again we are giving it heat. Okay, and due to that heat the temperature of the water will rise. till 100 degrees Celsius. Till 100 degrees Celsius the temperature of the water will rise. But after that what will happen? After that the temperature keep on rising till it reaches nearly 100 degrees Celsius, when it again becomes steady. Then it again becomes steady, that means it will remain at 100 degrees Celsius. Then the heat supplied now being utilized to change the water from liquid state to the vapor state. Okay, now why the temperature is constant? Because now the heat we are giving to water is not increasing its temperature. The temperature is remaining same, but that heat is utilized to change the state of the water to steam, or we can say vapor. Okay, and when the complete water will be converted into the vapor, again if we will give it heat, that will increase the temperature of the vapor. Okay, so the change of state from liquid to vapor or gas is called the vaporization, and it is observed that the temperature remains constant until the entire amount of the liquid is converted into the vapor. That is, both the liquid and vapor states of the substance coexist in thermal equilibrium during the change of the state from liquid to vapor, same as when we were changing the state from solid to liquid. So the temperature at which the liquid and the vapor states of the substance coexist is called the boiling point, and the boiling point of the water is 100 degrees Celsius. That means at 100 degrees Celsius the water will exist in both the states, in liquid form and in gaseous form. Let us do the following activity to understand the process of boiling of water. Take a round bottom flask more than half filled with water. Keep it over a burner. This is the flask and we have filled it with water. Okay. Take a round bottom flask more than half filled with the water, keep it over a burner and fix a thermometer and steam outlet through the cork of the flask. We have fixed this a thermometer, and this is the steam outlet from which the steam can get out. As water gets heated in the flask, note first that the air which was dissolved in the water will come out as small bubbles. Okay, when the water will be heated, the air which was dissolved in the water, some air will be dissolved in the water now, so that air will come out first as small bubbles. Okay, then later bubbles of steam will form at the bottom, but as they rise to the cooler water near the top, they condense and disappear. Now what will happen? We are started heating from the bottom now. So first, from the bottom layer the bubbles of the steam will form. That means at the bottom point, when this temperature will be at 100 degrees Celsius, and these molecules have taken the latent heat also. That means they have converted the phase from water to gas. Okay, so these molecules of water started converting into the steam bubbles or vapor bubbles. Okay, then their density is decreased now, so they will rise up. Okay, they will rise up, and after rising, what will happen? Here the temperature will be less, so what will happen? They will condense again and they will be converted into a liquid again. Okay, so the bubbles of steam will form at the bottom, but as they rise to the cooler water near the top, they condense and disappear. Finally, as the temperature of the entire mass of the water reaches 100 degrees Celsius, now when the entire mass of the water will reach 100 degrees Celsius, then bubbles of steam reach to the surface and boiling is said to occur. When the complete mass will reach the 100 degrees Celsius, then only the boiling will start. Okay, boiling will occur. Okay, so the steam in the flask may not be visible. Steam which is generated in the flask now will not be visible, but as it comes out of the flask, it condenses as tiny droplets of water. When this steam will come out from the flask, it will convert it into the tiny water droplets, because here the temperature will be greater, so they will be converted into the liquid droplets and giving a foggy appearance. From that we can understand that the water is converted into the steam. If now the steam outlet is closed for a few seconds to increase the pressure in the flask, now if we will close this steam outlet, then what will happen? The pressure on the flask will be increased. In the flask will be increased. Okay, increase the pressure in the flask, and you will notice that boiling stops. Boiling will stop. More heat would be required to raise the temperature, depending on the increase in the pressure. So before boiling begins again, thus boiling point increases with increase in the pressure. That means if we will increase the pressure now, then boiling point will increase. We have to supply more heat to boil the water. Okay. So let us now remove the burner, allow water to cool to about 80 degrees Celsius, remove the thermometer and steam outlet. That means all over we are reducing the pressure again. Okay, we are reducing the pressure again. So close the flask with the all tight cork, keep the flask turned upside down on the stand and pour ice water on the flask. Water vapors in the flask condenses, reducing the pressure on the water surface. Now what will happen now? Immediately we are pouring some ice on the water. So due to that, water vapors in the flask will start condensing. If the water vapor will be condensed, okay, previously there were water vapors, so they have increased the pressure. But now if the water vapor will be condensed, now that means the pressure will be decreased. So water vapor in the flask condenses, reducing the pressure on the water surface inside the flask. So water begins to boil again. Now at a lower temperature. Now water started boiling at 80 degrees Celsius. Okay. That means if we will reduce the temperature, reduce the pressure, then the boiling point will be reduced. Okay. So water begins to boil again now at a lower temperature. Thus boiling point decreases with decrease in the pressure. If pressure is decreased, the boiling point will be decreased. This explains why cooking is difficult on hills. At high altitudes, atmospheric pressure is lower. Due to the pressure is lower, the water starts boiling at a lower temperature, so reducing the boiling point of the water as compared to that at the sea level. On the other hand, boiling point is increased inside a pressure cooker by increasing the pressure. If water will be boiled at a very fast rate, then it will be difficult for cooking. Because cooking is done if the temperature is increased. Okay, but if water will be converted into the steam, then how the cooking will be done? So atmospheric pressure is lower, reducing the boiling point of the water as compared to that of the steel oil. On the other hand, boiling point is increased inside the pressure cooker. So by increasing the pressure, hence cooking is faster. So the boiling point of a substance at a standard atmospheric pressure is called the normal boiling point. Similarly, in that case of the melting point. However, all substances do not pass through the three states: solid, liquid, gas. There are certain substances which normally pass from the solid to the vapor directly. We have seen that some substances directly converted from solid to the vapor state, and also the vice versa. Some are directly converted from the vapor to the solid states. The change from solid state to the vapor state without passing through the liquid state is called the sublimation, and the substance is said to sublime. Dry ice, that is solid CO2, sublimes. So also iodine. Okay, dry ice is directly converted into the CO2 in the gaseous form. During the sublimation process, both the solid and vapor states of a substance coexist at the thermal equilibrium. When sublimation is there, the solid is directly converted into the vapor. Then both the solid state and the vapor state will be at the thermal equilibrium. Okay. Now the next topic is the triple point. What is the triple point? The temperature of a substance remains constant during its change of state. We know that the temperature is remaining constant whenever the state is changing or phase is changing. A graph between the temperature T and pressure P of a substance is called the phase diagram or PT diagram. When we will draw the graph between the pressure and the temperature, it is called the PT graph or phase change graph. The following figure shows the phase diagram of water and CO2. These are the phase diagrams of the water and CO2. This is for water and this is for CO2. So Such a phase diagram divides the PT plane into a solid region, the vapor region and the liquid region. In this, three regions are divided. The region between these two lines is the liquid, the region between this and the x-axis is vapor, and the region between this line and the y-axis is solid. Three regions are divided in this graph. Okay, so the regions are separated by the curves. These regions are separated by the curves such as sublimation curve, that is BO. This BO, this is the sublimation curve. That means if solid will cross this line, it will directly convert it into the vapor. That's why it is called sublimation curve. Sublimation curve, then fusion curve AO and vaporization curve CO. This is the fusion curve for conversion of solid to liquid and liquid to solid, and this is the vaporization curve CO, till CO only, not from B to C, because BO was the sublimation curve. If they will cross this curve, liquid will convert it into the vapor and vapor will be converted into the liquid. This is the same for the CO2 curve also. Represent states. The points on the sublimation curve represent states in which solid and vapor phase coexist. Okay, these points, that means from B to O, on these points, that means on these temperatures, between these temperature limits and between these pressure limits, sorry, these are the temperature limits and these are the pressure limits. Between these pressures and temperature limit, now the phase will be solid and liquid both on this curve BO. Okay, sorry, solid and vapor both, they will exist in both the states. That means phase changing is occur on this curve, sublimation curve. Represent the state in which solid and vapor phase coexist. So the point on the sublimation curve BO represent states in which the solid and vapor phase coexist. Points on the fusion curve AO represent states in which solid and liquid phase coexist, and points on the vaporization curve CO represent states in which the liquid and vapor coexist. These are the points on which solid and vapor phase will coexist. These are the points on which solid and liquid phase will coexist, and these are the points on which liquid and vapor phase will coexist. Okay. So the temperature and pressure at which the fusion curve, the vaporization curve and the sublimation curve meet and all the three phases of a substance coexist is called the triple point. Scientists have observed that all three curves are meeting at a point O. Okay, at this point all the three phases will be coexist together. Okay, that means at this point O, all the three phases will coexist in solid phase, in liquid phase and vapor phase also. So this point is called the triple point. Okay, so the points on the vaporization curve COD, okay, this we have done. Okay, coexist is called the triple point of the substance. For example, the triple point of water is represented by the temperature 273.16 Kelvin and pressure 6.11 into 10 raised to power minus 3 Pascal. This is the triple point of water. At this temperature is 0.01 degree Celsius. Now that means it is 273.15 plus 0.01 Kelvin. That is 273.16 Kelvin. Correct? And the pressure is, at this point the pressure is 6.11 into 10 raised to power minus 3 Pascal. At this point, these are the temperature and pressure at which the water will exist in all the three phases. That is called the triple point of the water. And for CO2 it is minus 56.6 degrees Celsius and 5.11 atm. This is atm. Okay, at this point the CO2 will exist in solid, liquid and vapor phase. This is the triple point. The next topic is our latent heat, and it is the last topic. In section 11.8 we have learned that certain amount of heat energy is transferred between a substance and its surrounding when it undergoes a change of state. We know that when the state of the body is changing, some amount of heat is transferred between the substance and surrounding. That means till we are giving it heat, the temperature of the substance is not changing, but that substance is gaining the heat. So that heat goes under the change of state. So the amount of heat per unit mass transferred during the change of state of the substance is called the latent heat. Okay, the amount of heat per unit mass. That means for a unit mass, how much heat we are transferring during the change of state, for changing the state of that substance, is called the latent heat. For the unit mass, that means mass should be for 1 kg, how much, for example, for 1 kg of water, how much how much heat we are giving to the water from changing to the liquid state to the solid state. That means for converting it to water to ice, then we will take the heat from the water. Okay, then how much heat is given in that is called the latent heat of the substance for the process. For example, if heat is added to a given quantity of ice at minus 10 degrees Celsius, that means first of all ice is at negative 10 degrees Celsius and we are giving it heat. The temperature of ice increases till it reaches the melting point 0 degrees Celsius. When we will give heat, its temperature will increase to the 0 degrees Celsius and now it is also in the ice form. Then at this temperature, the addition of more heat does not increase the temperature. After this, if we will give more heat to it, the temperature of this will not increase, but its phase will be changed and it will be converted into the water, but the temperature will remain the 0 degrees Celsius. Okay, so heat doesn't increase the temperature but causes the ice to melt or change its state. Once the entire ice melts, adding more heat will cause the temperature of the water to rise, and after a complete conversion of ice in water, then again if we will pass it more heat, its temperature will increase. Then again the water temperature of the water will again increase. A similar situation occurs during the liquid gas change of state. The similar situation will occur if we are increasing the temperature from the 0 degree Celsius water. First, the temperature will be increased to 100 degrees Celsius, and then if we will give it more heat, first the phase of the liquid will be changed into the gas, but the temperature will not increase, it will remain at 100 degrees Celsius. Okay. So the heat required during a change of state depends upon the heat of transformation and the mass of the substance undergoing the change, because latent heat is considered for the unit mass. So how much mass is there, it will depend on that. Thus, if mass m of a substance undergoes a change from one state to another, then the quantity of heat required is given by m into L. M is the mass of that body and L is the latent heat. So m times latent heat will be required to change the state of a given mass of a substance. That means latent heat can be given by Q upon m. This Q is the heat required to change the state, where L is known as the latent heat and it is characteristics of a substance, and its SI unit will be joule per kg, because it is Q upon m. Q is the heat, mass is the in kg, joule per kg. The value of L also depends on the pressure. Its value is usually quoted at standard atmospheric pressure. The normal value we are using now, that is at normal standard pressure, standard atmospheric pressure. The latent heat for a solid liquid state change is called the latent heat of fusion. When we are changing the state from solid to liquid or liquid to solid now, then that heat is called latent heat of fusion, and that is denoted by LF. That is called latent heat of fusion. And that for a liquid gas state, if we are changing the state from liquid to gas or gas to liquid, the latent heat will be required is called the latent heat of vaporization, or denoted by LV. These are often referred to as the heat of fusion and the heat of vaporization. We also call them as heat of fusion or heat of vaporization. A plot of temperature versus heat for a quantity of water as shown in the figure. This is for the water. The latent heats of some substances, their freezing and boiling points are given in the table also. We are not checking the table here, we are seeing the graph. This is the graph This is the temperature on the y-axis and this is heat on the x-axis. Okay, when we are giving heat to water, its temperature increases. For example, it is in solid phase first, it is at minus 10 degrees Celsius, assume that. Okay, so from this temperature we started giving it heat. Due to that heat, the temperature will increase till 0 degree Celsius. Okay, then what will happen? 0 degree is the melting point now. So at this point, if we will give heat, we are giving it heat, but temperature is not increasing. So from this to this point, the water the ice is converted into the water, that means in the liquid form, and that heat is this much heat. This is the latent heat of the fusion for the water, 3.33 into 10 raised to power 5 joule per kg. This is the latent heat of water. Okay, then again what will happen? The complete ice is converted into water, then again we will give heat, again the temperature will increase, and at 100 degrees Celsius again what will happen? If we will give heat, then temperature will not increase. Okay, so this will be the amount of heat given to change the phase from liquid to gas, and this value is different. That means latent heat of vaporization and latent heat of fusion are different. They are not same. For converting the liquid phase to gas phase, the heat given will be different, and this is given by 22.6 into 10 raised to power 5 joule per kg. Then again, if we will give heat, it will again increase the temperature of the gas. This is the graph. Okay. Now note that when heat is added or removed during a change of state, the temperature remains constant, that the slopes of the phase lines are not all the same. We can see here, these are the slopes of the phase line. That means this much distance was for this much heat supplied for the phase change from solid to liquid, and this much phase change for the liquid to gas, and they are not the same, and these slopes are also not same. Okay, so which indicate that specific heats of the various states are not equal. Also the specific heats are also not equal. For water, the latent heat of fusion and vaporization are 3.3 into 10 raised to power 5 joule per kg and 22.6 into 10 raised to power 5 joule per kg respectively. That is, this much of heat is needed to melt 1 kg of ice at 0 degree Celsius, and this much of heat is needed to convert 1 kg of water into steam at 100 degree Celsius. So steam at 100 degrees Celsius carries this much heat, this much amount of more heat than water at 100 degrees Celsius. Okay, that means if we have water at 100 degrees Celsius and if we have steam at 100 degree Celsius, which is more dangerous? Steam will be more dangerous because it is having this much amount of more heat energy than water. Okay, this is why burns from steam are usually more serious than those from the boiling water. Correct? Now there is an example. When 0.15 kg of ice at 0 degree Celsius is mixed with 0.30 kg of water at 50 degree Celsius, we have mixed them both. If we will mix, then what will happen? You know better. The amount of heat gain will be equal to the amount of heat loss. So in a container, the resulting temperature is 6.7 degrees Celsius. That means finally they both are at the 6.7 degrees Celsius. Also the ice and also the water. Calculate the heat of fusion of ice. We have to calculate the latent heat of fusion of ice. And we are given that specific heat of water is 4186 joule per kg per Kelvin. So first of all, heat lost by 0.3 kg of water when its temperature falls from 50 degrees Celsius to 6.7 degrees Celsius. This much amount of heat will be given to the ice now. So this heat is lost by the water, and the change in heat is given by again ms delta T. M is the mass of the water, S is the specific heat of water, and delta T is the change in temperature, and this is calculated by 54376.14 joule. Now this much heat will be absorbed by the ice at 0.15 kg, and this heat will be absorbed in two forms, one in the form of the latent heat and the other will increase the temperature of the ice from 0 degree to 6.7 degree. Correct? This latent heat will be used to change the state from 0 degree ice to 0 degree water. Then the temperature of the water will also increase now from 0 degree to 6.7 degree, because 6.7 degree Celsius is the steady state at which the no heat transfer occur. Okay, so heat required to melt the first we are calculating the heat required to melt 0.15 kg ice into 0 degree Celsius water. That will be equals to m into Lf na, mass into the latent heat of fusion for 1 kg of water ice. So this will be the heat required to melt the ice, and we don't know the value of the latent heat of fusion. We will calculate this, and the heat required to raise the temperature is this ms delta T again. Now the ice is converted into the water now, so specific heat of water will be used. Specific heat of ice is different, but there is no use of that, that's why it is not required. Okay, so specific heat of water will be this 4186, and this value we will get 4206.93 joule. This is the heat gained by the water when we are raising its temperature from 0 degree to 6.7 degree. Now the principle of calorimetry, heat gained is equal to heat loss. Heat gained in two forms, in the latent heat and raising the temperature, and heat lost by the water will be this. By calculating this, we will get the latent heat of fusion of ice, that is 3.34 into 10 raised to power 5 joule per kg. Now there is another example. Calculate the heat required to convert 3 kg of ice at minus 12 degrees Celsius capped in a calorimeter to steam at 100 degrees Celsius. We have to convert the 3 kg ice at minus 12 degrees Celsius to steam at 100 degrees Celsius at atmospheric pressure. Given specific heat capacity of ice, specific heat of ice is given, specific heat of water is given, and latent heat of fusion is given, and latent heat of vaporization or steam is also given. Okay, mass of ice is given, specific heat of ice is given, specific heat of water is given, latent heat of fusion of ice is given, and latent heat of steam is given. First what will happen, first we have to convert heat required to convert 3 kg of ice at minus 12 degrees Celsius to steam. Directly we have to convert the steam now, so we will convert in different forms. First Q1, we will first raise the temperature of ice from minus 12 to 0 degrees Celsius. That means it will be ms delta T. This amount of the heat will be required to raise the temperature of ice from minus 12 degree to 0 degree. Then what will happen? Now we have 0 degree Celsius ice. This will be converted into the 0 degree water. That means here the latent heat of fusion will be used, m into Lf. So heat required to melt ice at 0 degree Celsius to 0 degree water will be m into Lf. Latent heat of fusion is given, mass we know 3 kg. So this much amount will be required to convert ice into water, 3 kg ice into water. Now again the heat we will give will increase the temperature of water to 100 degrees Celsius. So this will be ms delta T. Now specific heat of water will be used, SW, and this will be given by this much amount. Then again heat required to convert the water at 100 degrees Celsius to steam at 100 degrees Celsius. That means again the heat will be given in the latent heat form, that is mass into latent heat of steam, and this will be given by this value. Then we will add up all these heats and we will get the final answer. That means this much amount of heat will be required to convert 3 kg of ice at minus 12 degrees Celsius to 100 degrees Celsius steam. Okay, this was the complete for this chapter. We will start the new chapter tomorrow in the class. Okay, thank you all.